When you are taking into consideration that the fact that your tasks or activities have variability in the time estimates, then we have to use this method here. So the previous method we looked at considered that we knew exactly how long it took to lay a foundation or pick out paint. But what if there's variability in those times? Well, then what we first need to do is we first need to identify the critical path. And we can do that by looking at the estimates that are most likely. So if we're not quite sure how long it takes to lay a foundation, pick out paint, we're going to need a range. We're going to need an estimate that's the most likely amount of time, and then we need an optimistic estimate and a pessimistic estimate. So what we need is a bit of a range. Now, your book, I believe, uses O for optimistic and P for pessimistic. Here we're going to use A and B, and that's because we'll use the P to represent the project. Okay. So first, identify your critical path based on the most likely time estimate. So that's here, this activities 1, 2, 4, 7 that we identified before. But now we have some optimistic and pessimistic times, the A and the B column that you see here. Well, to help us figure out the probability of completing our project by a certain time, we need to actually use the beta distribution. So the beta distribution comes from stats, and we don't need to know a whole lot in this class about the beta distribution. What we really need is just these formulas here. We need a way to calculate the average and the variability. Well, in a beta distribution, if you take 3 standard deviations in each direction, so that's where that 6 comes from, and we're going to more heavily weight the most likely estimate, which is why in this formula for the mean you see 4 on the M, we can use that to calculate the expected time for each activity. So for activity 1, for example, we could take 1 plus 4 times 3 plus 4 and divide the whole thing by 6. So it's taking an average like you normally would, but it's putting a heavier weight on the most likely estimate. So if we do that calculation, 1 plus 12 plus 4, and then we divide that by 6, we get 2.83. And we would repeat this for the activities that are on the critical path. So for activity 2, we would take 1 plus 4 times 2 plus 3. So 1 plus 8 plus 3 and divide the whole thing by 6. And that gives us a 2. We would do this to find the average or expected time for each activity, taking into consideration that there's variability in the times it might take. So take a moment and do for activity 4 and activity 7. All right, so you should have found 3 for activity 4 and 1 for activity 7. Notice that activity 7 has no variability. The optimistic estimate is 1, the pessimistic estimate is 1, and so of course the average estimate will be 1. To get our expected project completion time, we need to add those numbers up. 2.83 plus 2 plus 3 plus 1. So we get 8.83 months. Now that number is an estimate. So if we take into consideration the variability, we can then come up with the probability of being complete by a certain time. So we're going to need to calculate the variance for each of the activities. So we take the two extremes, the most pessimistic and the most optimistic, and you can find the variance using this formula here. Sigma squared equals B minus A divided by 6, and then squaring the whole thing. So if we're going to find sigma squared for activity 1, then we need to take 4 minus 1, divide the whole thing by 6, and square it. So we have 4 minus 1 is 3 divided by 6. That's a half. We're going to square that and you get 0.25. So sigma squared for activity 1 is 0.25. And we're going to repeat that for the activities that are on the critical path. So activity 2, let's put it over here, sigma squared 2 is going to be 3 minus 1, all divided by 6, and then square that. So that's 2 divided by 6, or a third, and you're squaring a third, and you get 0.11. Okay. So take a second and do the same calculation for activity 4 and activity 7, finding the variance for each activity. For activity 4, you should find that the variance is 0.44. And for activity 7, because the pessimistic and optimistic are the same number, your variance is 0. Now we want to know what the probability of completing the house is, so we need to combine this together to figure that out. So the next thing we need to do is find the project standard deviation. Oops, we seem to have shifted our things here. These numbers back in the right spot. Assuming we can. Put those back up there. And put these back here. Okay, so we want to find sigma p for the project. And we find that by taking the square root of the sum of the sigma squares. So we need to add up the 0.25 wherever it went. So 0.25 plus 0.11 plus 0.44 plus 0. So we add all that together. Okay. And then we're going to take the square root of that number. So we get about 0.8. If you include all the decimals from those previous sigma squares, I think you end up around, what is it, about 0.806? And we take the square root of that. So the square root, so we find sigma p, which was the square root of our 0.806. It comes to 0.898. And we found that the expected project completion time, we found that that was about 8.83 months. Now, why did we go through all this work? Well, what we really want to know is the probability we're going to complete our house in a certain amount of time. So what's the probability, for example, that we can complete this house in less than 10 months? To do that, we need to turn this into a Z-score. So we take the time we're wondering about, so we think we can get done in less than 10 months, and that 10 is the X in your Z-score. The mu is that expected project completion time. So we do 10 minus 8.83, and we divide that by the standard deviation of the project. So that was the 0.898. And if we do that calculation, I believe we end up with about 1.3. So we have a Z-score of 1.3. What do you do with this Z-score? Well, if we go to a standard normal table, we can look for a Z-score with that number. Now, when you look at standard normal tables, probabilities are on the inside and the Z-scores are on the outside. So here, these are all negative, so we'll skip that and go to the next page. And we're looking for a Z-score of 1.3. So we go to 1.3, And if you have more decimal places in your Z-score, you would keep going across. So if we're 1.33, we would be here. If it's 1.30, we're here. So what is the probability that we will finish this house in 10 months? Well, that's this 0.90 here. So the probability we would complete the house in less than 10 months is 90%. If we got a Z-score, let's say we got a Z-score of 1.85. 1.8, we go over to the 1.85, and the probability of finishing the house would be 96.78%. If the Z-score was 0.59, we go 0.5 over to the 9, and the probability of finishing the project would be 72%. So if we can take that variability from each activity, get an estimate, so your t and your sigma squared for each activity, and then we can turn that into expected completion time for the project, so t with a p, and the project standard deviation, we can then turn it into a Z-score and find the probability of completion. So in this particular example, the probability of being done in less than 10 months was 90%.